In this video, we're going to go over the most missed problems from the Best Fit Models assignment. Starting with this one, we have a child attached a spool to a kite and started to fly the kite. The elapsed time in seconds and the length in feet of the string between the spool and the kite is shown in the table below. So let's just get a picture for what's going on here. So we've got a person flying a kite. Okay, so they're holding the spool. We'll say this is their spool of yarn, and then they have the kite is up here, right? So we also need to take note that the length of the string is what is listed as our Y value, right? So the length of the string is our Y value. So notice that as the time increases, so after 2 seconds, 4 seconds, 6 seconds, and so on, so the time is increasing. So as time goes on, what's happening to the length of the string, right? So as time moves on from 0 to 10 seconds, the length of the string goes from 50 to 100. Right? So as time increases, the length of the string is also increasing. All right. What information is provided by the slope of the linear equation that models this data? So it's just asking us, what would the slope represent? So the kite ends up 50 feet from the spool. The kite starts 50 feet from the spool. So both of these would be potentially talking about the initial value or the y-intercept. So it wouldn't be either one of those. Part C, the kite is being released at a rate of 5 feet per second. Or D, the kite is being reeled in at a rate of 5 feet per second. So let's think about if the kite is being released. So if the kite is being released, that would mean that the string is getting longer, right? So if you're reeling something in, then the string would be getting shorter. So the slope for this, since we already know that the length of the string is getting longer, so it would be released. All right, let's look at the next one. The next one that was missed was the number of bacteria present in a lab is growing rapidly, and the table shows the number of bacteria after each minute. So first we need to know that X represents the number of minutes and Y represents the number of bacteria. All right, so if this exponential trend continues, how many bacteria would be present after 12 minutes? So 12 minutes would be your X value. And we're told that this is exponential. So we can find the exponential model for this by putting this table into Desmos. Right. So just to remind you what I have put into Desmos, I put in the table, then typed y1 squiggle a b to the power x1. So exponential best fit I'll remind you. In Desmos, you have to add your table, and then in a new box, type y1 squiggle a times b to the power x1, and you have to click log mode. Then we can write our equation, y equals a times b to the power x, using the a and b from Desmos. So a is 65.1004. B is 2.17152 to the power x. And then we want to know if this is the exponential trend. That means we started with about 65, and then we're multiplying 65 by 2.17152. So it's this number times this number, and then we keep repeating multiplication by this number over and over and over again. So if we multiplied by 2.17152, if we multiplied by that number 12 times, in other words, our exponent is 12. That would represent our 12 minutes. Then we can put that value into Desmos and see what it's equal to. Right, so the number I got was 715,730 bacteria. So that is closest to this approximation 709,000. And where the difference comes in, and you'll see this quite a bit, if you're not told to round to a decimal place, then I would take as many decimals as you can. But the difference here comes from how many decimals you chose. So for instance, if I only put a couple of decimal places, so let's say I did 65.1 times 2.17 to the power 12, notice that is 709, 737, so that's much, much closer. So it really just depends on your decimal places. The more decimals you put, or the more decimal places that you put, the more accurate your number is. So technically 715 is a more accurate number than 709,000, but it just depends on how many decimal places you put. All right, let's look at the next one. Right, in this one we have that the table shows the number of apples an orchard harvested in different years. What is the residual for the number of apples actually harvested after 15 years? So residuals, let's remind ourselves what a residual is. So a residual is equal to the actual Y value minus the predicted Y value. Okay, so if we have a table already created and you want to know the residual for a value that's in that table, so we want to know the residual after 15 years. Okay, so here's our information for 15 years. So in this table, this tells us that in year 15, there were actually 1,847 apples harvested. But we want to know how many apples were expected to be harvested in year 15. So we can put this table in Desmos, and Desmos actually will tell you the residual for a predicted amount. So if this fits a linear function, okay, so if this fits a linear function, then we would type y1 squiggle mx1 plus b. And when we do that, then this little button pops up that says residuals. So when I click this button, notice what happened in my table. I got a new column. So what these residuals mean is that these are the differences in the actual amount of whatever the y value was minus the predicted amount for that y value. So in year 15, it says that the actual amount was 1,847 and the residual is negative 19.7. So if you can see that number here in my table in Desmos where it says 15 and then 1847 and then negative 19.7, that means that 1847 was the actual y value, and whatever the predicted y value was, they had a difference of negative 19.7. That means that they actually harvested 19.7 less apples than expected. Okay, so I'll make a quick note of how to find that in Desmos. Okay, so first put your table in, y1 squiggle mx1 plus b, and then you're looking at this button that says E1 plot. You click that button, and then you're looking at column E1 in the table. All right, and the last one. Who earned the tips closest to the amount predicted by the line of best fit? So we have some different waiters, some people who worked in a restaurant, and the hours that they worked and the number of, or the amount of the tips that they earned. So who earned the tips closest to the amount predicted by the line of best fit for this data? So in other words, this is asking who has the lowest residual. So same process as the last one. We'll put this table into Desmos. Type in our linear model, y1 squiggle mx1 plus b. And then plot our residuals. So the person with the lowest residual was 1. Because Juan's E1, or his residual, was negative 12.6. So that means he earned $12 less than expected on average. So that means he earned $12.6 less than expected. Jeff earned $14.3 more than expected. Victor earned $48.2 less than he expected, and TJ earned $46.5 more than expected. So the closest person the person who earned the amount closest to what was expected for them to earn was Juan. He was only $12 off.